Okay, hello, good afternoon, everyone. So Mr. Lau here again. So what I'm going to do here today is to do some practice or revision question for graphing techniques. Okay, of course, due to the limited time, I will only be covering the first part of graphing first. All right, not inclusive of the transformation part. Okay, we'll cover the transformation part in another session. All right, so I've selected a few questions which I feel is important, and there is a few learning pointers, okay, that we can take back. Okay, so without further ado, let's look at the first question over here. Okay, this is from MJC. So we have a curve which has this equation. All right, and so first part, we are asked to use an algebraic method to find the set of values that y can take. Okay, so this is a very standard set of questions. So what we are going to do for part one, sorry, let me just take out my pen. Okay, so for part one, very simple. Okay, we will start off with the original equation itself over 3x plus 7. Okay, so what we are going to do here, we are going to cross multiply. All right, so cross multiply, this will give me 3y x plus 7 is equals to x squared plus 14x plus 50. Okay, so we're going to shift everything to the left hand side in an attempt to make a quadratic, okay, a quadratic equation. All right, so this will be x squared plus 14 minus 3y x plus 50 minus 21y. Okay, so if you take a closer look of how I write this equation, okay, this quadratic is in terms of x. Okay, so x itself is considered the variable. All right, and I placed all my y in the coefficient. Okay, can so the technique that we are going to apply for this question is that we are going to use b squared minus 4ac must be more than or equals to 0. Okay, I will explain this in a while. Let me just shift something. Okay, can so the b square over here will be 14 minus 3y square minus away 4 times a, which is 1, times c, which is 50 minus 21y. Okay, more than or equals 0. All right, so if you open this up, this will simply give me 9y square minus 4 more than or equals to 0. Okay, so we can factorize this using a square minus b square. So this will be 3y minus 2 times 3y plus 2 more than or equals 0. Okay, so we're going to draw the number line. Okay, so the two values will be negative 2 over 3 and 2 over 3. All right. Okay, so we put in the test value. This will be positive, negative, positive. So the values we are going to get here is y more than or equals to 2 over 3 or y less than or equals to minus 2 over 3. All right, so this is the answer for the first part. Okay, so actually why are we doing this? Okay, the importance of this method, okay, actually lies in this step. Okay, can because when we start from the first part, all right, what we are saying is that we are equating a horizontal line y to my equation. Okay, so if I were to draw a random graph here, it doesn't have to be correct. Okay, can so let's say the graph looks like this, and if I have a horizontal line, okay, we call y. Okay, so if I want to find the set of values of y can take, okay, so imagine this y can be shifted up and down. All right, so when in the regions whereby there is y values, okay, these are the regions whereby I will be expecting an intersection. Okay, same thing. These are the regions whereby expecting a intersection. So back to our initial way we solve this question, we are equating a line, a horizontal line, to my existing equation. So what we want here to find out the y values is we need intersections. All right, we need intersections. So for intersections to take place, simply we need to set real roots. So when there is real roots, okay, we simply use the discriminant b squared minus 4ac and set it to be more than or equals to 0. Okay, so this value here will tell me what the y values can take. Okay, so of course, if you look at these two values, there's actually a significance to this value. Okay, if you use back the same diagram I have here, you can infer that this y value here, okay, is going to be 2/3, and this y value here is going to be negative 2/3. Okay, so this method actually also enables us to find the turning point. All right, so but don't go and do your differentiation lah. Okay, because what the examiner or the assessment criteria is trying to test you on is actually this method. All right, so keep this in mind. These are my turning points. We'll use this later on. Okay, next for part 2, so we are asked to find the equations of asymptote. So to find the equation of asymptotes, of course, standard step, we must do long division. Okay, so long division, x squared plus 14x plus 50 divided by 3x plus 21. Okay, so to eliminate the x squared, put 1/3 x here. Okay, so this will be x squared plus 1/3 x times 21 will be 7x. So this will be 7x. Okay, so to get the other one, okay, to eliminate the 7x, all right, to eliminate 7x, we must 7/3 here. So 7/3 times 3x will be 7x, plus 7/3 times 21 will be 49. Okay, so the remainder will be 1. So to complete this, okay, this will be 1/3x plus 7/3 plus 1/3x plus 21. Okay, so to get a asymptote, very simple. All right, we ask ourselves two questions. All right, so when x approach infinity, what happens to y? So when x approach infinity, all right, this terms tends to 0. Okay, so y will tend to the line 1/3x plus 7/3. Okay, next, when x next when y approach infinity, or how do I make y to infinity? To make y infinity, the denominator, wherever it is, must approach 0. Okay, so 3x is approaching minus 21. X must be minus 7. So therefore, the asymptotes are y equals to 1/3 x plus 7/3, and x is equals to minus 7. Okay, so these are the asymptotes. Very standard stuff. You must know how to do it. All right, so with that, we will proceed to drawing the graph. Part 3, drawing the graph. Okay, so if you need, you can press the calculator to give you the shape. Okay, but for those who have followed me, you know that there's no need. Followed me physically in the class, you know that there's no need for the GC. You'll be faster to draw it by hand. Okay, so let's put in my asymptotes first. So we have x is equals to minus 7. All right, and then we also have my oblique asymptote. Okay, my oblique asymptote will be here. Okay, which is y is equals to 1/3 x plus 7/3. Okay, take note, they should be intersecting at this point. It must be shown, all right, because the x-intercept for this is also -7 if you work it out. All right, so there's supposed to be 2 turning points. All right, so let me just draw the graph. Okay, one will be somewhere here and the other one will be somewhere here. All right, so the 2 turning points, you can use your calculator. All right, go to your trace function there and find out your maximum and minimum point. Okay, so you should get the 2 maximum and minimum point. So this one here will be -6 2/3, and this one here will be -8 2/3. So take note of the y values here. It's exactly what we calculated just now, 2/3 and -2/3. All right. Okay, the next value that we need to put in also is my y-intercept. Again, from the calculator, you can get this is 50/21. Okay, and so that's about all. So this is my graphs. Okay, so next part 4, hence solve for this inequality. So how do we solve for this inequality? This inequality requires us to solve for this 50/x plus 7. Okay, so the standard method to approach this kind of question, all right, is to make my current graph, which is this one, appear on my left hand side. So you realize that it is almost there. Okay, just short of a 3 below. So the 3, you can shift it from the right hand side, x squared plus 14x plus 50/3 times x plus 7 less than or equals to 1. So we just shift the 3 across. Okay, so the left hand side is what we have. Okay, but of course over here we have a modulus here. Okay, so we can actually open up this modulus. So what we want here, okay, is we want to find the parts whereby this graph is in between -1 and 1. Okay, so you need to draw graphs on the existing graph that we have here. So the lines that we're going to draw is y equals to -1 and y is equals to 1. Okay, so let me draw it just okay, so this is y equals to 1. All right, and this will be y equals to -1. All right, so you have to use your GC, okay, to find out the coordinates of these 4 points. Okay, so the region that you want is for this graph to be between -1 and 1. So it's actually this region here and this region here. Okay, so these 2 regions are the one that fulfill the inequality. Okay, so let me just write down the answer. Okay, so using your GC, you can find the intersection between 1 and -1 with your existing graph. So the values you'll get, x is between -9.62 and -7.38, or x must be between -6.62 and -4.38. Okay, so some calculator work is required, right? You're supposed to apply it to get this intersection. Okay, so this will be the answer for part 4. Okay, other than that, very simple question. Okay, very standard. All right, just to bring your attention to part 1. Okay, you must know how to solve this. Okay, so that's it for this question. Let's move on. Okay, so for this second question, okay, we have the question that deals with your parametric equations. Okay, so for this example, I wish to show you how to work with parametric equation, and honestly, it's nothing much different from how we work with Cartesian. Okay, it's just that we need to go through the intermediate values. Okay, so let's look at part 1. how do we find the x and y intercept? So just like how we do in the Cartesian domain, okay, to find the x-intercept when y equals to 0. Okay, so we are going to look at the y equation, which is y equals to 9 over t minus 1. So we set 0. All right. So over here, t, if you work it out, it will be 9. Okay, so using this t value, we'll sub it into the x equation. So this is what I mean by you need to go through the intermediate values. Okay, you need to go through and find your t. And in this case, you'll get x equals to minus 2. So your coordinates here will be minus 2 and 0. Same thing for y-intercept. We find it when x is equals to 0. All right, so same, we'll equate this to the x equation, t squared plus 144. All right, and we will try to solve for my t. Okay, shift everything over, bring the square root over. So t here, if you do it, simple calculator, what you get 5. And then you will take this 5 and sub it into the y equation. You will get 0.8. Okay, so when you write down the coordinates, it will be 0 and 0.8. Okay, the t equals to 5 doesn't have to appear. Okay, so it's the same way we start off for the Cartesian equation. All right. Okay, when x-intercept when y equals 0, y-intercept when x equals 0. Okay. Okay, let's move on. Part 2. Given that the dy dx is this, explain why C has no stationary points. Okay, so dy dx is equals to 9 square root of t squared plus 144 over t3. Okay, so you must know that what is the condition for stationary point? For condition for stationary point is that dy dx must be equal to 0. Okay, so this question here involves logical interpretation of the equation itself. So the question is, can this be equals to 0? All right, under the pretext of what? Given that t is more than 0. So actually, it's very logical. Given that t is more than 0, okay, dy dx must always be more than 0. Okay, just look at where t's are. The t's is here. So if this is more than 0, the numerator will always be more than 0. If this is more than 0, the denominator was more than 0. Therefore, dy dx will just be more than 0. No further explanation is needed. All right, that's it. So part 3. So since therefore no stationary point, no stationary point. Okay. Part 3, state the value of x when t approaches 0. Okay, can so same thing. All right. So what we are going to do here is we are just going to set t to approach 0. So since we are interested in the x value, so x will approach 13 minus 0 plus 144. Okay. So this value here will be 1. Okay, so when t approaches 0, x will approach 1. It's just a mere substitution of t equals 0. Next, when t approach infinity, okay, what is the value for y? Okay, so when t approach infinity, all right, the value for y will approach, supposedly, you're not supposed to write this. Okay, I'm just going to write it down for the sake of teaching. 9 over infinity minus 1. So 9 over infinity here, you should be able to know that this is 0. All right, so this is minus 1. Okay, can. So, but if we look a bit further, okay, t approach infinity, okay, x itself will approach, okay, it's supposed to be 13 minus infinity plus 144. So this here is going to be a very big number. It's going to be negative infinity. So therefore, we say that x will approach negative infinity. Okay, so we are going to use all this information to do part 4, which is to sketch the graph. Okay, let's see how everything turns out. Okay, so let me just erase this and let's do the sketch of the graph. So of course you can use your GC, okay, but make sure, you see, as I say, the GC is not 100% reliable, okay, due to the resolution. Okay, sometimes it will mispresent certain information. All right, so you must make use of whatever that you have studied over here. Okay, can. So today, all right, this piece of information, okay, as x goes to negative infinity, y approach -1, this is actually a representation of asymptote. Okay, so you should be looking at y equals to -1 asymptote. Okay, can. Same thing for this case. For the top case, t approach 0, x approach 1. Okay, so if we again work backwards from here, t approach 0, all right, the y value is 9/0 minus 1. So again, if you are well versed in this, you should know that 9/0 is infinity. So actually this approaches infinity. So again, this here represents another asymptote at x is equals to 1. Okay, so we are supposed to make use of this information to draw out some features of the graph. Okay, so in part 1, we also have the intercepts and everything. Okay, so we are just going to use the GC, okay, together with whatever that we've calculated. Okay, this point here will be -2, and this point here will be 0.8. Okay, so this will be my parametric graph. Okay, nothing too difficult. Main thing is you need to apply back how you used to do it for Cartesian, but you have to go through the t value. All right, so this is a must know. Okay, let's move on. Okay, to the next question. Okay. Okay, so we have this question. Graph is given. So we have the sketch of this equation. Okay, we have this sketch of this equation. Okay, B, C, and D's are unknown. Okay, we are given a asymptote x is equals to -4 and y equals to 3x plus 2. Okay, so we are asked to write down the values of D and the values of B. Okay, so we are supposed to infer from the graph. Okay, can. So of course, we will just start the way we usually start because we are given a improper fraction. Okay, can. So the first thing that we are going to do here is to do a quick long division. All right, so the long division answer will give you 3x plus b minus 12, okay, plus this c minus 4 times b minus 12 over x plus d. All right. Okay, so how are we going to infer the values of d and b? So d, okay, we're going to infer from the vertical asymptote. So for the vertical asymptote to happen, x plus d must be 0. So x must be equals to minus d. Therefore, d must be 4. Okay, and same, next we're going to infer the b value from the oblique asymptote. So today, 3x plus b minus 12 must be eventually written as 3x plus 2. All right, so b minus 12 is equals to 2, so b must be 14. Okay, can. So this is how we infer the d and b value, okay, from the graphing properties. Okay, can. So that's it for the first part. Very simple. Okay, for second part, given that the curve has a stationary point, x equals to -2, find the value of c. So we're going to use the last property, which is to differentiate it. Okay, can. So we're going to use this 3x squared. So we're going to sub in the values for b. So b was determined to be 14. okay, plus 14x plus my c, which is unknown, times x d was 4. Okay, so we do dy dx. Okay, so we're going to do quotient rule. Put down the quotient first. Okay, differentiate the numerator, so it'll be 6x plus 14, minus away, do the other way around, so 3x squared plus 14x plus c, and then differentiate the denominator, which gives you 1 over x plus 4 squared. Okay, so since we know that x equals to minus 2 as a stationary point, we need to say that if we sub in x is equals to minus 2, okay, overall the equation should give you 0. Okay, so the simple trick here is I only focus on the numerator, because in order for this to be 0, the numerator has to be 0. So I sub in minus 2 plus 4 times 6 times minus 2 plus 14 minus 3 times, sorry, should be inside. Okay, will be 3 times minus 2 square plus 14 times minus 2 plus c, which give you whole thing 0. Okay, so from here, you can work out c to be 20. Okay, so we are asked then to find out the rest of the coordinates of the stationary points. Okay, so we will use back this equation that we have here, which is the numerator. Okay, which will be x plus 4, 6x plus 14, minus 3x squared plus 14x. Now we have the value of c, which is 20, and set it with 0. Okay, so we solve for x. In this case, it will be a quadratic. You can solve it yourself. X will be minus 2, and the other x will be minus 6. All right, and the corresponding y value you have to find for them also. The first y value will be 2, and the second y value will be negative 22. All right, so this is how you get your pair of your stationary coordinates. Okay, simple. Okay, next, we're asked to find the range of values of k for which this equation has no real roots. Okay, so how are we going to do it? Find such that this equation, so this the equation, let me write it down again. Okay, so this is as per the same kind of question as the previous round. Okay, we have to make use, we must change the left hand side to whatever that we have, which is this. Okay, so it's very easy. We just have to bring the x plus d over. Okay, so we want the intersection of this graph and this graph to produce no real roots. All right, so we have to plot y is equals to k on the existing graph. Okay, so y equals to k today is unknown, so we're just going to draw a horizontal line over here. Okay, so again, same thing, we can shift the y equals to k up and down. So we want the regions whereby it has no real roots. Okay, so at most, we can only shift it up to here. And at most, we can only shift it up to here, which is at the turning points. Okay, so when the turning point is here, this is y equals to 2. And this one is y equals to minus 22, as found just now. All right, so long as k retains between these two values, there will never be intersection. So from here, we can easily see that k must be between minus 22 and 2. All right, but no real roots. Okay, next, let's move on to part 3. Verify that the intersection between the two asymptotes lies on the line of this. Okay, so the intersection between the two asymptotes, okay, where is it? It's here. Okay, so how do we work it out? So we just equate one to the other. So y is equals to 3x plus 2, and x is equals to minus 4. So we sub it in. So y is equals to 3 times minus 4 plus 2, which is minus 10. Okay, so the intersection point here is minus 4, minus 10. So does minus 4 and minus 10 lie on this line? How do we know? We sub it in. So the left-hand side will be minus 10, correct? The right-hand side will be m times x, which is minus 4, plus 4m minus 10, which is also minus 10. Therefore, minus 4 minus 10 lies on y is equals to mx plus 4 minus 10. Okay, shown. Okay, so but what is the idea of this question? All right, this is an important question. Let's see. Hence, state the range of values for which the equation has two distinct real roots. So you see, it's the same way it's being asked, but today we are asked for two distinct real roots. So we are going to start off with the same thing. Write down the equation. Okay, is equals to m minus x plus 4 square plus 10x minus 40. So same thing, we are going to make the left-hand side look the same as this. So we already have the numerator, we only need x plus d. Okay, d today, okay, we have already found out to be 4, correct? D was found to be 4. So how can we do it? Okay, so we are going to shift this, we need to shift the, oh, okay, other than that, there's also a few other differences, right? The equation itself is also different. Let me take a look. Let me see, 3x squared minus bx plus c. Wait, give me a minute. Let me take a look. Okay, there is no way we can put them exactly the same. Okay, because for now the numerator, okay, the numerator clearly has its differences. So this is plus bx. Okay, we will deal with this later on. Okay, so but for now we know that d is 4. So we need to bring the something like x plus d to the bottom. Okay, can. So but you see, the thing is the right hand side. Okay, there must be a purpose for the previous equation, which is this one. So the left hand side, the right hand side must look like this. Okay, so to do that, okay, what we can do is to factorize out my x minus x plus 4. Okay, so if you take out the minus x plus 4 from the right hand side, okay, inside I'm left with m times minus x plus 4 plus, if I take out minus x plus 4 from here, all right, we are simply going to leave ourselves with minus 10. Correct? Because if I take minus 10 and multiply back by minus x plus 4, it will give me my 10x minus 40. Minus 10 times minus x is 10x. Minus 10 times 4 is minus 40. All right. So don't touch the left hand side first. All right. So then I'll bring over this minus x plus 4. M minus x plus 4 plus minus 10. All right. Can, so we want, so what this equation wants here is we want this intersection to have two distinct real roots. Okay, two distinct real roots. All right. So, but the problem here is that we do not exactly have what we are being given. Okay, what is the issue here? Okay, the issue, as I say, is the, let me change color, blue. Okay, so the issue here is there's a minus here, there's a minus here. Okay, even for this one, there's additional minus here. Okay, so based on my graphing techniques, we know that we can actually make a substitution, okay, to change the entire equation. So the substitution that we're going to make here is simply x is equals to minus x. So x is equals to minus x. It will not affect my 3x squared because x to minus x, square it, the minus will disappear, but it will change my bx minus bx to bx. C will not affect over x plus 4 is equals to mx plus 4 minus 10. So if I were to do this substitution, I can change entirely to what we have here. Okay, and this substitution over here is, what does it correspond to? What is this substitution? This is actually for those who have learned transformation, is actually a reflection about the y-axis. Okay, so if it is a reflection about the y-axis, all right, the x value will actually change. Okay, because currently what we have is this. Correct. This is what we have in the diagram here. All right. So if you take a closer look, this is the left hand side of this is the graph that I already have. How about the right hand side? The right hand side, m value is unknown. Correct. M value is unknown. Okay, but you see, if I'm going to do a random check, because previously I already proved that this equation, okay, will cut through this point here. Okay, so it is something based on experience that if I try to let m be 3, all right, so this will be y is equals to 3 x plus 4 minus 10. All right, and this will land us with 3x plus 2. So what is this? M equals to 3. M equals to 3 will give us this single member over here. Okay, can you see? This will give us a single member over here. Okay, so this member here will give me m is equals to 3. All right, and this single member belongs to the family of this. Okay, so when m changes, what happens? When m changes, the gradient of this family changes. If m increase, all right, if m increase, my gradient becomes steeper. And when m decrease, my gradient become more gentle. All right, so back to the point whereby I need two distinct roots. So if I need two distinct roots, do I want the gradient to be steeper or gentler? So do I want the gradient to move more than 3 or less than 3? So this is more than 3, this will be less than 3. So you see, for the more than 3, I will have one intersection, two intersection. For the less than 3, there will be no intersection. So therefore, we clearly want m to be more than 3. Okay, what I need here is clearly for m to be more than 3. All right. So, but then the question is, we haven't dealt with the transformation yet. the transformation of x is equals to minus x, which is a reflection about the y-axis. Okay, meaning to say the whole graph will be flipped around. So instead, let me just erase this. Instead of drawing this way, the whole thing is flipped to the other side. So we have this. Okay, we have this, and we have my graph, which is going to be looking this way and this way. And same thing, my member is going to be this. This was before we do the substitution of x equals to minus x. So this is still, in this case, this will be m. If I flip the whole thing, okay, if I flip the whole thing, what is this m value? This m value, okay, in this case, is it negative or positive? If I flip the whole thing, it'll be negative, right? So this gradient here will be -3. All right. So again, we want the intersection to happen, meaning to say that I must rotate the member this way. All right. So I'm supposed to make it even more negative. Correct. I'm supposed to make it even more negative. So if I want that to happen, all right, because now it's already downward sloping, I want to make it even more downward sloping. So this m here will be less than -3. Okay. So let me summarize what I've said all together. Okay, let me use a different color. Okay, we started off with this equation, which is what the question wants. We want this equation here to have two distinct roots. So we manipulate it until it comes to this point, which is the intersection of this graph and this graph must give you two intersection. But we do not have these two graphs. Therefore, we made a reflection about the y-axis to get to this point. So when we made a reflection to get to this point, the analysis becomes that of this graph. Okay, so based on the analysis of this graph, okay, to have at least two intersection, m must be more than 3. Okay, but this is not what we want yet. This is not what we want yet. Because in order to do this, I have reflected about the y-axis. Therefore, to get back the original, I must reflect the whole thing back about the y-axis. And it gives me this. All right, and it gives me this. In order for me to have two intersection, all right, my gradient must go the other way around. It must become more and more steep. So therefore, m must be less than -3. Okay, Ken? So if that's okay, that's the end for this question. Okay, most importantly, you must understand the idea of a member of the graph. Okay, the family of a graph. In this case, by setting m equals to 3, okay, you can literally find a member of the graph. And from there, you do the analysis. Okay, so if this is okay, let's move on to the last. Oops. Okay, to the last question, which is this SRJC question. So, okay, so for this question, we are going to sketch a quick oblique conics. Okay, so what we have here is what is this? It's a hyperbola. It's not hyperbola, sorry. It's a ellipse. Okay, so ellipse. So change it to the standard form. It should be x squared over root 6 square plus y squared over root 3 square is equals to 1. Okay, and then we have this also. All right, so same thing. I will do a quick long division. Okay, so this one will be y is equals to 1 plus minus 4 over x plus 4, x plus 2, sorry. So we are asked to draw these two graphs on a diagram. Okay, so let me make a quick sketch. Okay, so this one you can use your GC. All right, so for the ellipse, all right, the center is at 0, 0. Okay, and the x radius is root 6. Okay, and the y radius is root 3. All right, so we're going to draw this graph in the below axis. Why? Because they have already told you y must be less than or equals to 0. Okay, so this point here, since it's the y radius, okay, this point here will be your root 3. This point here will be your root 6, and this point here will be your negative root 6. Okay, so that's all for the first part. For the second part, all right, we're asked to draw this graph, okay, which is a rational function. Okay, so a few things that you need to draw in is your asymptotes. Okay, so we have y is equals to 1. We have x is equals to minus 2. All right, so we draw the graph. You can use your GC to get a shape. All right, and then we have this. Okay, so we are asked to list out all the intersections also. Okay, so this one here will be equals to minus 1. Okay, so that's it. We have the two graphs. So the first, for part 2, we are asked to solve this inequality. Okay, so the inequality x minus 2 over x plus 2 more than or equals to minus root 3 minus x squared over 2. So again, we try to correlate to what we have. The left hand side, we have it. How about this right hand side? What is this right hand side? The right hand side is actually the hyperbola that we have. Hyperbola. Sorry, why am I keep saying hyperbola? The ellipse that we have. Okay, it's the ellipse that we have. All right, so how do we know? We can actually do a quick manipulation. So y squared over 3 is equals to 1 minus x squared over 6. Okay, make y the subject and you will get the plus minus square root of 3 minus x squared over 2. Okay, there's a plus minus in front, but now since we only get the negative part as shown in the graph, the negative part only, so we only take the negative part. So we want this graph to be more than this graph, the blue to be more than the red. So which region? The blue is more than the red. Okay, so of course, there's only a certain region that the red exists, so we must shade it accordingly. So from here, this part is what we want. The blue is more than the red. Okay, and this part is what we want. The blue is more than the red. Okay, so we need to go to the GC to get out certain values. Okay, more importantly is this value over here. Okay, the intersection. All right, this intersection here will be minus 0.515 and negative 1.69. All right, so what's the answer? Okay, so for this first region, x must be between minus root 6 and minus 2. Or the second region, x must be between negative 0.515 and root 6. Okay, and there must be an equal sign. So this root 6 can be equal, and this root 6 can be equal. Okay, and this minus 0.515 can also be equal. Okay, -2 cannot be equal because -2 is the vertical asymptote. All right, can. So part 3, deduce the range of this. So from here to here, you can easily see that it's a substitution of x is equals to mod x. So therefore, for part 3, okay, I'm just going to reuse the solution here. So for part 3, okay, so we are going to do the same substitution. We're going to add the mod here, add the mod here. Okay, so by logical analysis, this is invalid because a modulus of x cannot be negative. So the only thing can happen is this one. Okay, but this again cannot happen entirely because modulus of x means it must be positive. Correct. So we can actually ignore the second part. So the final we have is modulus of x less than or equals to square root 6. And therefore, the final answer will be x must be between minus root 6 and root 6. Okay, Ken. So, well, today I've covered a few variety of questions, okay, which I think is important. Okay, hopefully you learn from this session. Okay, thank you so much, and I'll see you again.